Dear colleagues, let me welcome you at today's Theoretical Physics Seminar, or a farewell lecture. And our speaker for today is Vladimir Balek, who will tell us about the history how Max Planck discovered quantum.
Thank you. So, the topic of my farewell lecture is origins of quantum mechanics, and I would like to dedicate the lecture to my two teachers. First of all was Jan Pichut. He was from here, from our department, and he introduced me to quantum mechanics, and then the second teacher, Jiří Bičák, led me out into general relativity. Sadly, both these perfect scientists and perfect people are not among us anymore. So I was involved in general relativity during my professional life, but I was in contact with quantum mechanics too. I even have written a paper on the quantum mechanics of Big Bang. It was published in proceedings of a conference called 100 Years from Einstein in Prague. The main organizer was Jiří Bičák. He gave that conference as a present to himself to his 70th birthday. So, what do we know? What everybody knows about the creation of quantum mechanics. We know that the creator was Max Planck, and he explained in the year 1900 the spectrum of blackbody radiation, so that he first proposed a simple interpolation formula for it, and then he derived the formula from the assumption that radiation is emitted and absorbed by quanta. He took as sources of radiation resonators. So these are harmonic oscillators which interact with radiation predominantly on their resonance frequency, their natural frequency, and he determined the spectral density of the intensity of radiation from the mean energy of resonator with the natural frequency equal to that of the radiation. And it turns out that the spectral density in equilibrium should be proportional to this mean energy. I will speak about that later. And in order to compute the energy, mean energy, he needed to count states of the resonator. And for that purpose, he needed to discretize the energy. That means to divide it into some small intervals delta E. And in the end, these intervals should vanish from the theory. It was known already from the way how Ludwig Boltzmann explained the thermodynamics of ideal gas. But it turned out that they do not vanish. So the question is why? In part one, I will explain how this mean energy is computed and why this elementary interval of energies does not disappear, stays in the formula. And in part two, I will show how this energy converts to spectral density, bringing this elementary interval of energy into the Planck's law. So, part one, computing the energy of resonator. So let us look on this Boltzmann's effort, how he formulated the statistic of ideal gas in the year 1877. So this will be his rendition of this theory. We have today a bit different version, although the thermodynamics which was obtained by Boltzmann is the same. Why I would speak about some theory that do not hold anymore. Jan Pichut spoke about such approach to didactics that, for example, when one starts explaining quantum mechanics by Bohr's model of atom, that it is the method of rusty nail, that you first put the nail into the plate, wooden plate. That is the Bohr theory, Bohr model of atom. Then it rains, snows, etc. And then the nail becomes rusty and cannot be pulled out. But still, I wanted to do that because just in order that you can somehow how it is the phrase, obuť si topánky, ako sa povie, to somehow to feel how was this feeling of Planck when he created quantum mechanics. He had only this theory, nothing else. And here is the picture. with molecules that are the balls numbered from 1 to capital N. And then there are energy layers, which by Boltzmann, they were just boxes. Nowadays, the energy layers are shelves, and within them there are boxes representing states. Here it's like there is only one state, and molecules can stay in some state. The arbitrary number of molecules can be there. So this was Boltzmann's theory, and the total number of distributions of these small balls into the boxes, Boltzmann called them complexions, is n factorial. The number of shuffles in each box is each box is ni, and that means that the number of different distributions, because this stage you have here some indistinguishable particles, but some distinguishable particles, but indistinguishable states within the energy layer. So you can shuffle these balls as you wish, and effectively you achieve in this way indistinguishability of the molecules. And so this ni factorial for the ice box, and that means that the number of different distributions is n factorial of the product of all these ni factorials. So this was Boltzmann's formula for the number of states of a molecule in an ideal gas. And now we proceed as we are used to, that we use a string formula, and then we can introduce the probability that a particle arbitrarily taken from this set of n particles will be in the ice energy layer, and then the entropy can be written in a way very similar, what we know how Shannon's entropy looks like, that it is minus capital N, and then this is multiplied by the sum of products, probability times the logarithm of probability. So this was Boltzmann formula. I did not pay due respect to Boltzmann because I did not put there his constant. Boltzmann constant is by me is 1. So And now we look for the maximum of entropy at given total number of molecules and total energy of molecules. So we can use a standard method of Lagrange multipliers, and we can see that we have such a nice exponential expression for the probability. So the dependence on energy is correct. Well, it's not clear by now that it is correct, because there is this constant beta in front of energy, which cannot be seen at all, but it is there. And what is beta? So we can determine it by thermodynamics only. We need not any kind of kinetic theory of gases, because we have some, when we search for maximum of entropy, we have some variation of entropy, sum of two terms with Lagrange multipliers. Term proportional to variation of number of particles, and another proportional to the variation of energy. And this we can simply compare to the change of variation, or change of the entropy by reversible process, which we know from thermodynamics. It is also some of such two terms when we put volume constant. And we can surely give these two quantities into equality, because on the left-hand side is difference of entropies, which one is in equilibrium and another one is in arbitrary state near to equilibrium. Generically, it is a non-equilibrium state, but it can be an equilibrium state as well. So this is how we arrive at these two well-known values for the Lagrange multiplier, that alpha is minus chemical potential over temperature, and beta is inverse temperature. So that the second result tells us what I already stated in advance, that this dependence of probability on energy is correct, but the problem is with this first Lagrange multiplier, this alpha, that if we would try to normalize probabilities with the alpha we know from thermodynamics, it would not work. And the problem is that we need for this probability, it is not pure thermodynamic. We need some microscopic picture behind it. And that microscopic picture was not correct by Boltzmann. But when we look at the entropy, total entropy of the gas, we discover the same expression as we see in the textbooks today, so that the entropy is correct, and as a result, the whole thermodynamics is correct within this strongly simplified theory of Boltzmann. Okay, so let us pass to the thermodynamics of resonators. That is to the article by Boltzmann from the year 1900, and I have here a long quotation from the article where Planck shows respect to Boltzmann. He says that when he wants to evaluate entropy of resonator, he tried to do that within thermodynamics. I will come to that on my last slide. But all he obtained was this interpolation formula without any deeper justification. So that is why he came to the conclusion that this entropy will be determined by the way in which the energy is distributed at one time over many resonators, and that he needs to use the procedure for this computation, which was developed by Boltzmann. He specifically refers to this article from the year 1877. So, here is the picture for the computation of Planck, that we have again balls and boxes, but now they are interchanged because balls are energy intervals and boxes are resonators. And we distribute these intervals among resonators. The total number of interval is fixed. That means the total energy of a resonator, and also total number of resonators is fixed. And of course, now I have there these little numbers. These are ordering number of the intervals, but of course all the intervals are equal. There are no more equal between them, among them. So we can shuffle these balls within their boxes as Boltzmann, but we can shuffle them also between boxes. So that the formula is now different. Everyone knows the formula because this is how one derives the Bose-Einstein distribution, so that the number of distribution is now the binomial n minus p over n. It can be again rewritten with the help of Stirling formula, and we can now write the entropy. I have written already, as Planck does, the entropy of one resonator. It is known that one can do it. You need many particle system to define entropy in a general case, but for ideal gas, you can introduce also this one particle entropy. So it is expressed here in terms of this small n, which is the ratio of the numbers capital P, capital N, that is number of intervals over the number of resonators, so that it will give the mean energy of the resonators. And this second expression, capital U is the mean energy of a resonator, and epsilon is this energy interval. So this is how this interval, which vanishes completely from the thermodynamics of ideal gas, this is how he is here to stay in the thermodynamics of oscillators, just because of this exchange of balls and boxes. And there is some elementary algebra. Then we could again find the maximum of S, but it is easier to write the inverse temperature, this coefficient beta, as a derivative of entropy with respect to energy, and by such kindergarten algebra we obtain the expression for the mean energy of the oscillator, which we know from this formula, from this Planck's law. But now there is not so far there is not this natural frequency of the resonator. There is this interval of energy in this formula, and it will be converted to frequency after we will find this how this mean energy is related to how it is related to spectral density of intensity, and after we invoke the Wien's displacement law. This is how frequency enters there. So far, there is only this epsilon. So this is part one, and now I have quite a lot written about this second topic, about how to convert now this energy to spectral density of intensity, but I know that I have only 12 minutes, so I will try to compactify it somehow. I have here this definition what the resonators are. A charge oscillator immersed in radiation, which are damped just by radiation they emit themselves. So that we have this elementary equation for damped and driven oscillator. Damping, there is damping coefficient gamma in the second term on the left-hand side, and omega 0 is natural frequency, and there is this E parallel, that is just projection of the electrical intensity to the direction of the oscillator. So this is quite trivial. Perhaps a bit interesting is the question: what is the size of the damping? What value is of this gamma? So one should go back to Landau-Lifshitz, the classical theory of fields, paragraph 75, where there is the explanation how this damping works. There is some force of radiation reaction, the formula with third derivative of the displacement, and from that we find the expression for gamma, that it is proportional to the classical radius of the particle, which for electron is only a bit more than 2 Fermi. So it is a very small length, and here is the warning that the theory works only on scale as much greater than this length. There are some paradoxes like self-acceleration of the particle. So we obtain from that condition, we obtain that gamma must be or is much smaller than the natural frequency. This, in fact, we have used when deriving the expression for gamma. And now, condition of equilibrium is that the energy of a resonator, which I now write as curly capital U, differentiated with respect to time and averaged over some large enough time interval, that this quantity, this dot U, is 0, and from that we can express this capital U, which is mean value of energy. So that is the idea of what one does next. So it's quite a lengthy calculation. It is easy. There are two terms, damping term and driving term. It is easy to compute this damping term, that it is just minus gamma carat capital U. But when we compute the driving term, that should be proportional to the spectral density of intensity. We must to suffer a bit. So I have written it here in 3 points. First, how it looks for monochromatic plane wave. It is still easy, but then we need to pass to general plane waves, so that some Fourier integrals appear there, and they must be somehow written by using some simplifications. First of all, when we compute the time average, we have some restriction on the natural frequency and on averaging time, but then when we want to simplify this, in fact, to discover there this spectral density, we need one more assumption, that the radiation is natural. What it means is written here. Some integral condition, and with that we obtain spectral density already in this expression for this driving term, but not spectral density of intensity, but of some quantity J, which is called by Planck also intensity, that it is intensity of excited oscillations, but in fact it is energy density, something like 4 pi times the part of energy density which participates in driving the oscillator. So we must then consider some of waves in different direction, and then only we arrive at this quantity curly I with the index omega is the spectral density of intensity. And here is the relation between these two spectral densities. The one which we found in the expression for the driving term, and another one which we want to have there. So we can now revisit the condition of equilibrium, the equality of the two terms in the rate of change of energy. And we have here it is in two slides there, and the end is this spectral density of intensity, that it is equal to some coefficient times mean energy of the resonator with the natural frequency equal to the frequency of radiation. So, and we can now write Planck's law by using this fundamental assumption of statistical mechanics, that the average over time equals to the average over ensemble. So that this U, this mean energy, we now can insert for it the expression which was obtained by Planck a bit later from these distributions of balls between boxes. So here I revoke this formula with this epsilon, and here is the time to refer to Wien's displacement law, or invoke Wien's displacement law, and in this way we find that this energy interval, elementary energy interval epsilon, must be proportional to omega, and we have the expression for the spectral density of intensity, which we know from the lectures, for example, by Richard or by Peter. Is it that? Can be. Okay, and here is now this last slide. How far we can get with thermodynamics only. That was a very, very sophisticated theory developed by Planck before this article. And he was able, not knowing anything about the entropy of radiation, still only from the assumption that this system resonator and radiation is near to equilibrium. He was able to derive a formula for the time derivative of total entropy of the system, where we have now only this entropy of the resonator, the second derivative of it. And now we can compare two expressions for this derivative of total energy for n oscillator oscillators, and we find that this second derivative, which enters there. I apologize. There should be only a second derivative of S with respect to U without this delta U squared, and that it should be proportional to 1 over U. And from this was Planck able to derive mean distribution, but then it became clear that mean does not work for small frequencies. So he looked once more at this derivation. He said that in fact these two expressions need not to be so for this as thought differentiated so strongly restricted, so that we can have some more general expression for the second derivative of S with respect to U. And he proposed, and this was his interpolation formula, that instead of U in the denominator could be the product U times beta plus U, and that such correction works very well, fits very well the data. So that was Planck's discovery of quantum. I tried to a bit make you enthusiastic that Planck, in my view, he is such a formula-like theoretical physicist. Textbook example, when he saw this new problem which emerged then, that this blackbody radiation with some universal spectra which cannot be observed directly, but can be very easily pulled out from observations when you know the absorption coefficients in various modes of electromagnetic radiation when it is incident on the body you are interested in. There are no truly black bodies. A black hole is not a absolute black body, because when you let the waves ingoing wave to come to it, some of it always goes to infinity. Only part is swallowed by the black hole. But we have this ideal object, Platonic object, this black body radiation, and it is a great challenge to explain it. And so Planck succeeded in that. So I must say to him, "You are really cool, Max." That's all.